Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. I'm an extreme skilled research computational mathematician. On the 4th of July, 1989, I experimentally discovered that massively parallel processing many initial boundary value problems arising in calculus and massively parallel processing the system of equations of algebra that approximated those problems and massively parallel processing them at once instead of sequentially processing only one initial boundary value problem at a time should be the starting point of the modern calculus, extreme scale algebra, and the massively parallel processing supercomputer. I experimentally discovered that parallel processing should be embodied within most computers and across all supercomputers. That experimental discovery is my contribution to the development of the modern computer that now computes in parallel. That experimental discovery changed the way we think of the supercomputer. In the old way that was used since 1946, the supercomputer solved only one initial boundary value problem, such as the general circulation model used in climate studies at a time. In the new way that I experimentally discovered, the modern supercomputer solves millions upon millions of initial boundary value problems, such as petroleum reservoir simulations arising in modern calculus and extreme scale computational physics, and solves them in parallel or at once. The toughest problems in modern calculus can only be solved by dividing them into numerous problems and then massively parallel processing them across a network of tightly coupled processors that were already available in the market, with each processor operating its own operating system, and with each processor having its own dedicated memory that shared nothing between each other. Since 1946, over 25,000 supercomputer scientists tried to parallel process the toughest problems in calculus, algebra, and physics. Those 25,000 supercomputer scientists failed to experimentally discover how to parallel process, or died trying to figure out how to parallel process. In April 1967, Jean Amdahl, who was the most respected supercomputer scientist of the 1960s, came up with his often quoted Amdahl's law. In a nutshell, Amdahl's law advised supercomputer designers such as Seymour Cray to give up on their ever-elusive dream of trying to design the massively parallel processing supercomputer hopeful that will be crowned as the fastest supercomputer in the world. For over 2 decades, Seymour Cray and the supercomputer community accepted Amdahl's law as the uncontested truth. In April 1967, Jean Amdahl argued that the massively parallel processing supercomputer cannot be harnessed and used to solve the toughest problems that arise from the modern calculus. Such grand challenge initial boundary value problems arise as the primitive equations of meteorology that are used to forecast the weather. Such grand challenge problems is the recurring decimal in the extreme scale algebraic problems of the modern computational mathematician. Such grand challenge problems arise from the excruciatingly detailed computational physics models that must be solved to foresee otherwise unforeseeable climate changes. Seymour Cray, the uncontested leader in the field of the vector processing supercomputer, agreed with Jean Amdahl that the massively parallel processing supercomputer will forever remain a huge waste of everybody's time. Steve Jobs later told the New York Times that his parallel processing computer that is powered by only 8 central processing units is extremely difficult to program. Steve Jobs believed that it will be impossible to harness the total supercomputing power of thousands of tightly coupled processors that were already available in the market anyway. Steve Jobs believed that it may be impossible to use the technology of the massively parallel processing supercomputer and use that technology to solve the toughest problems arising in science, technology, engineering, and mathematics. Why is parallel processing seemingly impossible to the likes of Steve Jobs? My complete answer to this grand challenge question of what makes the supercomputer super is extremely difficult to understand. It took me the decades of the 1970s and 80s to arrive at the frontiers of knowledge of mathematics, physics, and supercomputing. It took me those 2 decades to understand parallel processing, the technology that was the big overarching question in modern computer science. For that reason, I did not expect Steve Jobs to understand how to massively parallel process and to understand the technology within only 1 year. Asking me to give you a 60-minute lecture of what makes the supercomputer super will be to asking me to reply to an email message, and to do so before I've actually read the whole email message. I'm Philip Emeagwali. I began my quest for the fastest supercomputer, and I began that quest on the first supercomputer to be rated at 1 million instructions per second. I began my quest for the fastest supercomputer on the early morning of Thursday, June 20, 1974, in Corvallis, Oregon, United States. After 15 years of that quest, I experimentally discovered the massively parallel processing supercomputer, and I discovered that technology at 8:15 in the morning of Tuesday, the 4th of July, 1989, at Los Alamos, New Mexico, United States. Put differently, parallel processing was impossible on June 20, 1974, but possible on the 4th of July, 1989. That is, the massively parallel processing supercomputer that I experimentally discovered was a future technology during the decades of the 1980s, 70s, 60s, 50s, and 40s. The massively parallel processing supercomputer was then a future technology, just as the quantum computer was a future technology in the 1990s. The massively parallel processing supercomputer was logically feasible in 1974, but the technology could not be harnessed until I, Philip Emeagwali, experimentally discovered the technology and invented that technology on the 4th of July, 1989. My contribution to the development of the modern computer is this: I constructively reduced to practice my new internet, that was my new global network of 65,536 tightly coupled, commonly available processors, and reduced that new internet to a new supercomputer that is a new computer. That experimental discovery made the news headlines back in 1989. The high-resolution general circulation modeling is the most vexing grand challenge problem in extreme-scale computational physics. The general circulation model transcends and traverses across calculus, algebra, computing, and across the new internet that I invented as a new global network of 2 raised to power 16 commonly available processors that were identical to each other and that were equal distances afar and apart from each other. That network of processors is de facto a supercomputer that is 16 orders of magnitude faster than a computer. To make that experimental discovery that encompasses the disciplines of mathematics, physics, and computing called for a polymath and not for a mathematician. That polymath must be a jack of all sciences and must be at the frontier of scientific and technological knowledge. That polymath must be a master of mathematics, physics, and computing. That polymath must know calculus and know it forward and backward and know it from the storyboard to the blackboard to the motherboard, and most importantly, know how to solve the toughest problems arising in calculus and know how to solve them across motherboards, that each is an ensemble of processors that computes as one seamless, cohesive supercomputer that is beyond super. I'm Philip Emeagwali. I'm a supercomputer scientist. I am an internet scientist. I am well known, but I am not known well. When I visit the public libraries in the United States, I often run into elementary school students or middle school students or high school students doing research report for their school reports. Some school reports were titled Famous Scientists and Their Discoveries, or Great Inventors and Their Inventions. Since my experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July 1989 and that made the news headlines, thereafter, many school reports had the title The Contributions of Philip Emeagwali to the Development of the Computer. Each school report on Philip Emeagwali presumes that the 12-year-old writer understood what he wrote about the precursor to the massively parallel processing supercomputers that I invented. Each school report presumes that the 12-year-old writer understood how I experimentally discovered the new massively parallel processing supercomputer and understood my detailed explanation that spanned thousands of pages that the new technology is a new internet, and understood my explanation of how the new technology makes the modern computer faster and makes the modern supercomputer fastest. That experimental discovery and invention of the massively parallel processing supercomputer took me 16 years onward of June 20, 1974 to understand. Therefore, it's impossible for a 12-year-old whose 42-year-old father was not born when I began programming the fastest supercomputers in the world back in 1974 to understand the massively parallel processing supercomputer that took me 16 years to understand. So a 12-year-old submitting a school report on the contributions of Philip Emeagwali to the development of the supercomputer is like the boy that looked at the tip of a faraway iceberg and told his father that he has seen the 90% of the iceberg that is underneath the surface of the ocean. 90% of my research on extreme scale computational mathematics that led to my experimental discovery of the precursor to the massively parallel processing supercomputer is dense, abstract, and as invincible as the 90th or 90% of the iceberg that is below the water's surface. Because only 10% of my invention of a new internet that was a new supercomputer and a new computer was understood, I am well known, but I am not known well. It's been said that sometimes you must leave home to understand home. I had to leave physics, where I began in June 1970 in Onitsha, Nigeria, namely the ordinary level physics of the General Certificate of Education of the University of London, England, as well as the advanced level physics of the School Certificate of the West African Examination Council of Lagos, Nigeria. After January 15, 1970, the day the Nigeria-Biafra War was over, growing up as a 15-year-old in my ancestral hometown of Onitsha, Nigeria, my knowledge of physics in 1970 was limited to the 1,118-page textbook that was titled Advanced Level Physics. That physics textbook was written by Michael Nelcon and Philip Parker. Both co-authors were physics teachers for the Advanced Level General Certificate of Education of the University of London, England. Advanced Level Physics was the most popular physics textbooks in British Commonwealth and was popular from India to Africa. I left physics through calculus. I left physics, taking with me the second law of motion that I encoded into my system of 9 coupled nonlinear time-dependent state-of-the-art and never before seen partial differential equations of the modern calculus. Those partial differential equations and my mathematical and experimental discoveries of how to discretize and solve them across my new internet, that is my new supercomputer and my new computer, was the cover story of top mathematics publications such as the May 1990 issue of the Siam News. The Siam News is the bi-monthly news journal of the Society of Industrial and Applied Mathematics, that is the top society for research mathematicians. As a polymath, a set of laws of physics was the lowest common denominator in the theories and experiments that I conducted during the 16 years onward of June 20, 1974. That was the first day that I programmed the sequential processing supercomputer that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States. In textbooks on computational physics, where there are laws of physics that were used to solve problems, there are systems of partial differential equations of calculus that encoded those laws of physics. Where there are partial differential equations of calculus to be solved on supercomputers, there are large-scale systems of equations of algebra that approximated those systems of equations of calculus. Where there are large-scale algebraic equations to be massively solved in parallel, there must be a set of floating-point arithmetical operations that solved those equations. For that reason, it made the news headlines that I experimentally discovered the precursor to the massively parallel processing supercomputer of today, and that I invented that technology on the 4th of July, 1989 in Los Alamos, New Mexico, United States. I experimentally discovered that where there are humongous sets of floating point arithmetical operations that takes 30,000 years of time to solution on only one isolated processor that was not a member of an ensemble of processors, that there should be a new internet, that is a new global network of processors, or a new global network of as many identical computers. That new internet is a new supercomputer and a new computer that takes just one day of time to solution to solve what otherwise will take 30,000 years to solve. The reason the 12-year-old is doing a school report on the contributions of Philip Emeagwali to the development of the computer is that I experimentally discovered how to massively parallel process and how to do so across a new internet. The reason my experimental discovery of the massively parallel processing supercomputer was written in major US newspapers was that my discovery opened the door for speeding up 30,000 years of time to solution on one computer that computed with only one processor to just one day of time to solution on one supercomputer that simultaneously computed across a tightly coupled ensemble of 10 million processors. My technological quest for the fastest supercomputer that began on June 20, 1974 in Corvallis, Oregon, United States, was for the shortest times to the solutions for the grand challenge problems of the massively parallel processing supercomputer that is a new internet and a new computer de facto. My quest was for the shortest time to solution of the most excruciatingly detailed general circulation modeling that must be used to foresee otherwise unforeseeable climate changes. The following are 6 facts about my scientific quest for how and why parallel processing makes computers faster and makes supercomputers fastest. That scientific quest was for the Philip Emeagwali formula that I experimentally discovered on the 4th of July 1989 and that United States President Bill Clinton reconfirmed in his White House speech of August 26, 2000. First, I began programming supercomputers at age 19. Second, I have been supercomputing since June 20, 1974. Third, I programmed supercomputers from the sequential processing supercomputer that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States, to the most massively parallel processing supercomputer ever built in the 1980s that was in Los Alamos, New Mexico, United States. Los Alamos, New Mexico, United States is to the modern supercomputer what Abuja is to modern Nigeria. Fourth, when I began programming supercomputers, there was no computer that I know of in sub-Saharan Africa. Fifth, when I began programming supercomputers, the word supercomputer had not entered into any dictionary. Sixth, when I began programming supercomputers, President Richard Nixon was living in the White House. Today, there is a computer in almost every White House in the United States and beyond. By the 1940s definition, and to some extent, we are all computer scientists. But not all of us can be listed by Google in the top 10 contributors to the development of the computer. Only one person experimentally discovered how and why parallel processing makes computers faster and super. My contribution to the development of the fastest computer is that I experimentally discovered that parallel processing makes computers faster and makes supercomputers faster and super, namely the Philip Emeagwali supercomputer formula for processing across processors. And that experimental discovery made the news headlines in 1989. In the 1970s and 80s, I struggled to write about my experimental discoveries that pertained to how to massively parallel process initial boundary value problems of calculus that arose in extreme scaled computational physics. My scientific maturity grew across the decades of the 1970s and 80s. For that reason, my clarity became sharper with distance in time and space. That distance made the massively parallel processing supercomputer once again strange, but as familiar as the sequential processing computer. The grand challenge problem in massively parallel processing supercomputing was a public examination problem that was given by the United States government and given in the 1980s to 25,000 vector processing supercomputer scientists and to their leader, Seymour Cray. That examination was a clarion call to solve the toughest problems that arose in extreme scale computational physics. Each of those 25,000 vector processing supercomputer scientists and their leader, Seymour Cray, gave up on the dream of being the inventor, to enter into the history book and enter as the inventor that solved that grand challenge problem of the massively parallel processing supercomputer. For me, Philip Emeagwali, that came of age in the early 1980s, the massively parallel processing supercomputer was a new theory or an idea that was not positively true. Back in the 1970s, the massively parallel processing supercomputer that I experimentally discovered on the 4th of July 1989 was a science fiction that demanded a new calculus and that demanded new calculations and that demanded new experiments that I executed across a new internet, that is a new global network of 64 binary thousand tightly coupled processors. That global network is a new supercomputer. That global network is a new computer. And most importantly, my experimental discovery that a problem in extreme scale computational physics that is impossible to solve on a sequential processing supercomputer is, in fact, possible to solve across a massively parallel processing supercomputer that is a new internet and a new supercomputer. As was reported in the US media back in 1989 and thereafter, only one supercomputer wizard passed that grand challenge examination. I am that lone wolf supercomputer scientist that passed that grand challenge examination. At its granite core, the fastest supercomputer is only fastest and super if and only if it computes in parallel to solve the previously impossible to solve. For that reason, the father of the fastest supercomputer is the massively parallel processing supercomputer scientist that experimentally discovered how and why parallel processing works. It's difficult to define the father of the massively fastest supercomputer that computes in parallel and that communicates across the millions upon millions of tightly coupled processors. The father of the modern supercomputer is the contributor to the fastest supercomputer that was at the farthest frontier of supercomputing. The father of the supercomputer was longest at that farthest frontier of supercomputing. The father of the supercomputer crossed the farthest frontier of the supercomputer and crossed that technological frontier at a time everybody else scorned, ridiculed, and rejected parallel processing and rejected the technology as a huge waste of everybody's time. Perhaps it is only at a very visceral level that you will recognize the father of the modern supercomputer. Back in 1989, 25,000 supercomputer programmers abandoned the precursors to the modern massively parallel processing supercomputer that computes across processors or across tiny computers. The leader in the world of vector processing supercomputer, named Seymour Cray, was the strongest opponent of the modern massively parallel processing supercomputer. To date, the brainiest quote of Seymour Cray is this, quote, "If you were plowing a field, which would you rather use? 2 strong oxen or 1,024 chickens?" Unquote. Seymour Cray would rather compute with 2 strong oxen. That was his metaphor for the 2 fastest processors in the world. I, Philip Emeagwali, would rather compute with 1,024 chickens. That was Seymour Cray's metaphor for the 1,024 slowest processors in the world. As was reported, including in the June 20, 1990 issue of the Wall Street Journal, I, Philip Emeagwali, experimentally discovered that 65,536 chickens are more powerful than 1 oxen. I experimentally discovered how the modern supercomputer that embodies millions upon millions of tightly coupled, commonly available processors becomes a cohesive whole unit that has no edges or directions. My experimental discovery of the massively parallel processing supercomputer opened the door to the fastest supercomputer of today. For the record, Seymour Cray ridiculed and caricatured the fastest supercomputer that computes in parallel. For this reason, Seymour Cray is not one of the fathers of the fastest massively parallel processing supercomputers that he ridiculed and caricatured. Today, the fastest supercomputers compute in parallel. You will know the father of the fastest supercomputer by watching his videotaped lectures on his contributions to how and why parallel processing makes the supercomputer fastest and super. The fastest computer is the supercomputer. My name, Philip Emeagwali, is associated with the world's fastest computer. A 12-year-old writing a school report on Philip Emeagwali asked me, who is the father of the modern supercomputer? I explained that the modern supercomputer is not a computer per se. To describe the modern supercomputer as an invention will be akin to describing a 1-mile-long bridge as an invention. The River Niger Bridge between Onitsha, Nigeria and Asaba, Nigeria is not an invention. A bridge is an engineering project, not an invention. However, a construction engineer can invent a never-before-seen bridge. The Hong Kong-Zhuhai Mekong Bridge of China is an engineering project in progress. It will cost $10.7 billion. The Hong Kong-Zhuhai Mekong Bridge is 42 kilometers long. It is one of the longest bridges above water. The Hong Kong-Zhuhai Mekong Bridge is not an invention of the bridge. The Gotthard-based tunnel is 35 miles long and 1.4 miles deep. It is a railway-based tunnel that goes through the Alps of Switzerland. The Gotthard-based tunnel is an engineering project that took 17 years to build. The Gotthard-based tunnel is the longest and the deepest train tunnel in the world. The Gotthard-based tunnel cost $12.2 billion. The Gotthard-based tunnel was not the invention of the tunnel. An engineering project differs from a technological invention. The 726 feet high Hoover Dam is an engineering project that will cost $89.7 billion in today's dollars. The Hoover Dam is not an invention of the dam. The London Crossrail is an engineering project in progress that will cost $23 billion. The London Crossrail is not an invention of the Crossrail. A supercomputer engineering project that employs 1,000 supercomputer scientists differs from a supercomputer invention made by only one supercomputer scientist. The fastest supercomputer is the biggest computing machinery ever built. The fastest supercomputer costs the budget of a small nation. The fastest supercomputer occupies the space of a soccer field and is de facto an ensemble of millions upon millions of tightly coupled commodity processors that talk to each other via email wires. So it's impossible for one person to build or invent the entire supercomputer that occupied a soccer field. But it is possible for one inventor to invent or to experimentally discover the new technological knowledge that makes the modern computer faster and makes the modern supercomputer fastest and super. What made the news headlines in 1989 was that I, Philip Emeagwali, that was described in the US media as the African supercomputer wizard in the United States, had experimentally discovered that the slowest 65,536 processors in the world will always be faster than the fastest vector processing unit in the world and be faster for solving the 20 grand toughest problems in supercomputing. Those toughest problems were posed by the United States government. My experimental discovery of the massively parallel processing supercomputer opened the door to its commercialization within modern computers and modern supercomputers. My experimental discovery that occurred on the 4th of July 1989 opened the door to using the massively parallel processing supercomputer to solve the most extreme scale problems arising in computational physics and solve them across thousands or millions or billions of processors that were already available in the market anyway. That commercialization of the massively parallel processing supercomputer reached into almost all modern computers and into all modern supercomputers. Briefly, my experimental discovery of the 4th of July 1989 that occurred across and within each of my 65,536 commodity processors inspired a team of 1,300 Chinese engineers and scientists to build the world's fastest supercomputer that computes across 10,649,600 commodity processors. I contributed to the development of the modern computer and the modern supercomputer. And I contributed when I experimentally discovered how and why parallel processing makes computers faster and makes supercomputers fastest and super, namely the Philip Emeagwali formula for recording the fastest supercomputer speeds. President Bill Clinton, described that Philip Emeagwali formula in his White House speech of August 26, 2000. I began programming supercomputers on June 20, 1974. That supercomputer was the first computer to be rated at 1 million instructions per second. That supercomputer was housed at 1800 Southwest Campus Way, Corvallis, Oregon, United States. On the 16th anniversary of my first day on that supercomputer, or on June 20, 1990, the Wall Street Journal reported that I, Philip Emeagwali, had experimentally discovered how and why parallel processing makes computers faster and makes supercomputers fastest and super, namely the Philip Emeagwali formula for recording the fastest speeds across the massively parallel processing supercomputer. I had been studying calculus daily and studying calculus for the 20 years that preceded June 20, 1990. So after those 20 years, I was at the forefront of mathematical knowledge of how to solve the most advanced partial differential equations of calculus and how to solve those equations and solve them across a new internet that I invented as a new global network of 64 binary thousand commodity off-the-shelf processors that were tightly coupled to each other. As a research computational mathematician, I grew during those 20 years. Overall, I knew more than any mathematician that was aspiring to solve the largest scaled problem in algebra. The proof is that the 24 million system of equations of algebra that arose from my discretization of a system of coupled nonlinear time-dependent hyperbolic and never before seen partial differential equations of calculus that are known as the Philip Emeagwali's equations that I solved in the 1980s made the news headlines, and did so in part because it was a world record in extreme scale algebra and in high performance supercomputing. My mathematical quest for the solution of the toughest problem in calculus was like searching for a black goat at night. Briefly, this is my supercomputing story. I experimentally discovered how to open the door that takes the modern calculus across a new global network of tightly coupled processors that were already available in the market that shared nothing, or across a new internet that is a new supercomputer and a new computer. That experimental discovery is my contribution to computational mathematics and to the modern calculus. That experimental discovery was the cover story of the June 1990 issue of the Siam News. The Siam News is the #1 publication for those applied and computational mathematicians that are interested in learning about new mathematics, such as new partial differential equations that have not yet entered into mathematics textbooks. At the National Computer Conference that took place in New York City from June 7 to 10, 1976, the foremost supercomputer experts warned that parallel processing machines will be too large and too clumsy and a huge waste of everybody's time. In the 1980s, I could count the number of computational mathematicians that were massively parallel processing and count them on my fingers. I know because I was logged on 24/7 on the most massively parallel processing supercomputer in the world. Today, that supercomputer will cost the budget of a small nation. I, Philip Emeagwali, was the most extreme scaled computational mathematician that programmed the most massively parallel processing supercomputer ever built. I programmed that supercomputer alone. Today, 1,000 supercomputer scientists program only one supercomputer. I was the lone wolf programmer of the precursor to the modern supercomputer because computational mathematicians were heeding the warnings that it will forever remain impossible to harness the power of thousands of processors. In the November 29, 1989 issue of the New York Times, Neil Davenport, the president of Cray Computer Corporation, the sister company to the company that manufactured 7 in 10 supercomputers, warned that, quote, "We can't find any real progress in harnessing the power of thousands of processors," unquote. In an earlier article that was distributed on September 2nd, 1985, and distributed to the print media, and distributed by the United Press International or UPI, and in that article, John Rollwagen, the president of Cray Research Incorporated, that was the company that manufactured 7 in 10 supercomputers, described his company's use of 64 processors as, quote, "more than we bargained for," unquote. I was the lone wolf supercomputer programmer of my new global network of 65,536 tightly coupled processors. I was the lone wolf because the supercomputer scientists of the 1970s believed that it will be impossible to use 64 processors and use those processors to cooperatively solve the toughest problems arising in calculus. The supercomputer scientists of the 1980s believed that it will be impossible to use 64 processors and use those processors to solve the most extreme scaled problems arising in algebra. The supercomputer scientists of the 1980s believed that it will be impossible to use 64 processors and use those processors to execute the computation-intensive floating point operations arising in arithmetic that I executed as the world's fastest computation and executed on the 4th of July 1989. I was the lone wolf internet scientist and supercomputer programmer of my new internet that comprised of my new global network of 65,536 tightly coupled processors that were already available in the market, that shared nothing, and that was 1,024 times beyond the perceived limit of the supercomputer industry. The computational mathematicians that read the supercomputer textbooks cited Amdahl's law to argue that parallel processing an initial boundary value problem of modern calculus and parallel processing those problems across an ensemble of 64 binary thousand processors would forever remain impossible, or at least remain impractical. I'm Philip Emeagwali. I'm keeping this conversation alive at emeagwali.com. It's been said that out of the heart, the mouth speaks. I've spoken a lot since the 1970s and spoken about how I witnessed the experimental discovery of the massively parallel processing supercomputer. The words I spoke came from my discoveries, heart and brain. I'm giving this lecture because I discovered that the fastest supercomputer must be powered by the largest ensemble of processors. I'm giving this lecture because I contributed to the development of the massively parallel processing supercomputer. I'm giving this lecture because I discovered how to solve the toughest problems arising in extreme scale computational physics. I'm giving this lecture because I discovered the massively parallel processing supercomputer that became the most expensive instrument of extreme scale computational physics. I'm giving this lecture because my experimental discovery of the massively parallel processing supercomputer was the inflection point that opened new possibilities in the world of the computer and in the fields of extreme scale computational mathematics and computational physics that must be used to foresee otherwise unforeseeable global warming, and that must be used to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas. My words in these lectures will define me for posterity. To witness a discovery that has rich, fertile, and far-reaching consequences is like walking into a forest and witnessing a lot of leaves fall on your head. Thank you very much. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.